Okay, so it's the last talk of the presentation today. I wanted to discuss with you a little bit my activity on passive radar using software-defined radio. And I want to use the opportunity to discuss a little bit about how to use GNU Radio to run some processing software that's not readily available as a processing block. So that's work that I started working on. I've been thinking for a very long time about passive radar, and I'll define, of course, what passive radar is. And I was lucky enough to spend the last winter in University of Sendai, in Tohoku University, where Weike Feng and Professor Motoyuki Sato introduced me to the actual implementation of signal processing for passive radar. And so we've been playing with this since I returned to France this year. So that's a bit the context. So what is passive radar? Passive radar is the idea that, okay, you all know radar. Radar is basically I send an electromagnetic pulse or a broadband signal. I'll discuss later why broadband. And this signal will get reflected by targets. And the first thing you can do with a radar measurement is to try to detect the range. So range is the distance between you and the target that's reflecting the signal. And then you can get a second information, which is velocity, because a moving target will introduce a Doppler shift. And so you get two information out of your radar measurement, which are range and Doppler. Now, the first thing you want to do in a warfare theater is get the emitter down, because you know that someone is going to detect your plane, your missile, whatever, or actually you moving around. And so if you have an active radar system with a dedicated emitter, that's the first thing you will shoot at when you start launching an attack. So there's a big trend lately, or actually lately, it's been a trend for a long time, but it's become more active to the general public lately, in that you would like to use the electromagnetic smog, all these emitters that we have around us, to do some radar measurements. So basically what I'm considering is what are the emitters, non-cooperative emitters, I will call them, lying around, and what sources can I use to do some measurements. So that's what is called passive radar. Passive radar is using all the surrounding radio frequency emitters as radio frequency source, and we are going to analyze the signal to try to extract information about velocity and range of targets. Now, radar communication, you might be familiar with one-way communication where you have an emitter, a receiver, and you know that there your link budget scales as the second power as the square of a distance. You have your link budget as 1 over d squared. The problem with radar is that we are emitting a signal from a source. It bounces on a target, which we assume to be a point-like target, so 1 over d squared. And this new source is emitting a spherical wave that gets back to your receiver. So this means that we don't have a d squared, but we have d squared multiplied by d squared. So in radar system, we have 1 over d to the 4th power. And so this means that your signal decays pretty fast. So what are the requirements? If I want to do passive radar, first of all, I need a rather powerful emitter, because now my link budget is not over 1 over d squared, but it is 1 over d over 4th power. So I need a powerful emitter. And the second thing is, I'll show you in the next slide, the range resolution is inverse of the bandwidth, more or less. So if I want a high range resolution, I need a broadband signal. So these are the two requirements I'm looking for. So what is a radar, a passive radar? A passive radar is made of one antenna facing the non-cooperative emitter. In this case, you cannot see it. It's a TV antenna located over there. So it's a 3 kilowatt TV antenna for terrestrial broadcast television. And we have one antenna facing this reference signal. And then we have the second antenna facing the other way around, trying to look at time-delayed copies of a signal that was emitted by this non-cooperative emitter. And what I would like to introduce you with is that, well, one of the very simple radio frequency receiver that we can use is actually an oscilloscope. Because for radar measurement, you don't want you don't need a continuous stream. We can just live with chunks of data that we are going to cross-correlate, because we want to look for copies, time-delayed copies of a signal. So you don't care about continuous stream. You can just catch 2 channels of, let's say, 4096 long samples, and we're going to process these. And even if these streams are non-continuous, well, we detect a target, and then we think a few milliseconds later, is the target still around? So I catch another bunch of data. So that's a bit the story. So I can do some passive radar measurement just with 2 antennas, preamps, and an oscilloscope. That's as simple as this. And so what is your estimator? What is the signal processing you need to run? Well, you're looking at a reference signal. This reference signal might be Doppler shifted, and it will be time delayed on your measurement channel. So your correlation, what you're looking at is, can I find the reference signal in time delayed copies of a measurement? So that's the tau here is time delay. So I have a signal that I sent, I have some echoes that are returned after some time tau, and I'm trying to slide the reference signal over the measurement to try to match these two signals. And because this measurement is that of a moving target, I might have some Doppler shift. So we end up trying to calculate the ambiguity function, which is called the measurement at time tau plus tau, integrated after multiplication with a reference signal multiplied by exponential of j2 pi Doppler shift. So it's as simple as this, doing a radar processing. Now, what I would like just to quickly go with you is to discuss what is passive radar measurement. And as part of my work at Fem2ST, I'm not looking at passive targets, I'm looking at sensors. So I will just try to quickly introduce to you the sensors I work with, which I characterize through their radar cross-section. I would like to show you how I can measure the sensor response, the radar cross-section of these sensors using GNU Radio. And I would like to show you how we can use passive radar using Wi-Fi emitters. And at the end, I will briefly show you, I will not get into the details because we've already seen people doing some DOA measurements, but I want to show you how passive radar is well suited for DOA analysis. So just to quickly, briefly show you what we're doing in Fem2ST. In Fem2ST, we have a capability, for those of you doing hardware, we've seen a bit of electronics. You might know that when you want to do some very sharp filters, when you want to do some fancy signal processing, well, there is one technique that is converting the electromagnetic wave into an acoustic wave, in a mechanical wave. And the reason for this, the rationale, is that acoustic waves are 10 to the 5 times slower than electromagnetic waves. This means that if you want to make a filter or resonator in which your wave has to travel multiple times your time delay, well, a coaxial cable introducing a time delay of 1 microsecond will be 150 meters long. An acoustic wave device will shrink this dimension by 10 to the 5, so it will be 1.5 millimeter long. So the rationale of making filters, making resonators, you might all be familiar with cross resonators when you clock a microcontroller. All these techniques using piezoelectric substrate to shrink the dimensions are the reason why you can make high efficiency filters in your mobile phone, and you don't have a mobile phone that is about 2 meters long, because you can shrink these dimensions by 10 to the 5 by converting electromagnetic signals into acoustic signals. So this means that in Fem2ST we have the means, technology and facilities for fabricating devices that will introduce 1 to 2 microsecond delay with millimeter long devices, where you would need a 300 meter long coaxial cable to delay a signal by 2 microseconds. We can make these with surface acoustic wave device, so using piezoelectric substrate that will shrink dimensions to only a few millimeters. So if you don't care about the physics, forget about the physics. If you just think that it's fascinating that you can make a 1 microsecond delay long on a 3 millimeter piece of material, just look at the time domain characterization. This is a time domain characterization. Of course, you cannot read the x-axis. This is going from 0 microseconds all the way to 3 microseconds. And you see I have here echoes. These are echoes. These are reflectors on my acoustic delay lines. And basically what I'm creating here, I'm creating artificial echoes. So instead of looking at passive reflectors, which are targets, I'm making a sensor made of 8 echoes on acoustic delay lines, and the distance, the time delay between these echoes is representative of a physical quantity that I would like to measure. If you just want to imagine, the time delay between these echoes is dependent on temperature, because temperature will shrink or extend my mechanical piezoelectric substrate, and so if I heat up or if I cool down my sensor, my substrate, I will change the time delay between my echoes. So basically, my work as my research activity is to design these sensors which are passive, no local energy source because they are irradiated by the radar, and I'm looking at the radar cross-section. No energy source, wireless, because I can connect these devices for an antenna. So these passive wireless sensors are interrogated through radar systems. Now, the company I used to work with has a big challenge in certifying these short-range radar systems. So what I'm trying to work on is, can I use passive radar to interrogate these devices? And this brings me to a bit of a side note, just to introduce you a core concept of signal processing, which is what is the characteristics of a signal needed for time resolution. So here are a few examples. These are all synthetic signals, and then I will go back to GNU Radio. I've put here the MATLAB or Octave command lines if you want to reproduce these simulations. So the first thing I'm doing is I have a continuous wave. So you might be able to see here on the slide, I'm sending a continuous wave, just CW carrier, and the Fourier transform of this continuous wave carrier is just a sharp delta Dirac. It's a sharp peak in the frequency domain, offset from the 0 hertz by the period or the frequency of this signal. Now, a continuous wave has no timing characteristics. You just cannot make any difference between this sine wave period and this other sine wave period. They're all the same. So how can I put some timing information in here? Well, one thing I can do is I can introduce some binary phase shift keying. So binary phase shift keying simply means I take 1 out of 2 periods and I flip the phase. So I start with 0 phase, and then at some point I decide, let's flip the phase. So I introduce 180-degree phase shift, then I flip the phase again, 0 phase shift. So 1 out of 2 periods, I flip the phase. You see on the spectrum, instead of having a single peak here, I have now a whole collection of structure in my spectrum, but still, these are discrete functions. These are discrete peaks. Discrete peaks in the Fourier domain means periodicity. Of course, now I can differentiate 1 out of 2 periods, but I still cannot differentiate this period and this one because it looks very similar to this one. So I introduced a little bit of timing capability, but it's not that great. So how can I do this even better? Well, rather than switching 1 out of 2 periods, I change 1 in n periods, with n being a pseudo-random generator. So we know how to create a pseudo-random sequence. It's just a linear feedback shift register. And this pseudo-random sequence will not repeat. If you have an n-bit pseudo-random sequence, it will not repeat below 2 to the n minus 1. So what you see now is that if I take the Fourier transform of this pseudo-randomly phase flipped sequence, now I have a continuous spectrum, and this continuous spectrum has been broadened. This is what is called spectrum spreading. If you want to introduce time resolution, you need to spread the spectrum. Now, on the opposite, if I want to time a signal, I need to dispread the spectrum. How do I dispread the spectrum? I take the correlation. The correlation is, here is the autocorrelation of a signal that I have just showed. If you take the autocorrelation of a continuous sine wave, you have no timing capability. So your correlation just looks flat. There is no way to differentiate one time from another because a sine wave always looks similar. If I put periodically flipped phases, well, you do see a bit of a structure. Now I can differentiate a few periods, but if you look on a longer duration, you have hardly any timing capability because, well, 1 out of 2 periods will look similar. And finally, if I take the autocorrelation of my pseudo-randomly modulated signal, now in the correlation function, I have a delta Dirac. So I mean I can time my signal with the inverse of a resolution, with a time resolution, which is the inverse of my bandwidth. So the final story here is you need to spread the spectrum if you want timing capability. If you don't have spectrum spreading, you will have no timing capability. Now, you might wonder, what is the relation between this spectrum spreading and timing capability? Here is an example of what is called a noise radar. Noise radar is, you have here a pseudo-random sequence generator, and this pseudo-random sequence generator feeds the intermediate frequency load of your mixer. Now, this means that a mixer that you either, if you don't polarize it, it will run the radio frequency signal through 2 of the diodes of one bridge, and if you polarize the bridge, you will run the radio frequency through the other 2 diodes of your rectifying bridge. So this means if I have here 0, I run 0 phase. If I have here 1, I have 180-degree phase. So a mixer is a BPSK, binary phase shift keying mixer, modulator. So I have my carrier frequency, I have my pseudo-random sequence generator, I send the radio frequency signal, and by doing this, I simulate a passive radar, a noise radar, because I collect on the reference channel a copy of the pseudo-random sequence that is sent over here, and my sensor is time delaying this pseudo-random sequence. So that if I now calculate the correlation, Well, here you see the correlation of my pseudo-random sequence, and you see here, these are the 8 bits that I showed you earlier of my sensor. So what you can do is you can make a timing capability, you can make a noise radar just with one mixer, and a local oscillator. Now, what I find quite nice with this setup is that you nicely differentiate the center frequency of your radar, which is defined by the local oscillator, and you differentiate it from the bandwidth, which is given by the bit rate of your pseudo-random sequence generator. So that allows you to nicely differentiate the two characteristics. The black curve here is the autocorrelation, where when there is no time delayed echo of a sensor. So you see here a pretty flat curve, which does not show the structures that we have here on the echoes. So that's the basics of passive noise radar, Now, how do you demonstrate this using GNU Radio? Now, using GNU Radio, what you can do is you can run the passive radar measurements. Here is an oscilloscope capture of the frequency band in Japan, in Sendai, where you have 5 gigasample per second. So that's actually quite a high-grade oscilloscope, radio frequency grade oscilloscope. And what I did here is I measure from minus 2.5 gigahertz up to 2.5 gigahertz. And here you see your TV stations. So around 500 megahertz are the TV stations. This is the mobile phone. So 870 megahertz is the mobile phone. And if you take the autocorrelation of the signal, well, autocorrelation will show you a peak whose width is the inverse of the channel bandwidth. So if you have 5 megahertz channel bandwidth, which is the channel width in Japanese standards, when you have an autocorrelation which is 200 nanoseconds, 200 nanoseconds is the inverse of 5 megahertz, and 200 nanoseconds will give you about 30 meter resolution, sorry. And then if I take a cross correlation between my surveillance channel and my measurement channel, so one channel is targeted towards the TV channels, the other one opposite, looking at the targets, you have here the cross correlation. The cross correlation shows some structure, and these structures are all the reflected signal from the surroundings. So it's quite easy to run these setup in GNU Radio. Now in GNU Radio, you do not have a correlation function. So what we do is we have written a block, which is an oscilloscope source. So this allows you to take any oscilloscope and to feed GNU Radio with the data stream collected from the oscilloscope. Again, I do not claim to have a continuous stream. You will not listen to FM station using the GNU Radio oscilloscope. You can do radar, because with radar you just need to have chunks of data and take this data for correlation. Now correlation, this will be the topic. I'm not showing you this chart here because that's the topic of a tutorial that I'm giving tomorrow morning. So tomorrow morning's tutorial is called Basic GNU Radio, because I'm not telling you anything fancy about GNU Radio. I get you introduced in GNU Radio, but I still think I can tell you a bit something new about the digital signal processing, including how to run some correlation measurement in GNU Radio using Fourier transform and inverse Fourier transform. Now, just to show you what it looks like, what I love with GNU Radio is that what I love with GNU Radio is that I can run my chart both on synthetic signals and on real signals. So just to quickly show you how do you compute a correlation, I'll show you tomorrow the mathematics, but the mathematics of computing a correlation is taking the Fourier transform. As Paul just showed us, if you want to take a Fourier transform, you need to accumulate enough data to compute the correlation, so to compute the Fourier transform, so you first convert your stream to vector. So the length of the vector is the equivalent of a pulse repetition rate when you're talking about radar, so how often you do the measurement. So you convert the stream to vector, you take Fourier transform, and I'll show you tomorrow during the tutorial that by taking the complex conjugate multiplication of the Fourier transform of a reference signal with the Fourier transform of a measurement signal, you get the Fourier transform of a correlation. So you can implement correlation with this free Fourier transform block. And what I like with GNU Radio is that you will run the same flowchart with either. This is my passive radar implementation using DVB-T receivers. So we discussed with a few of you during the demonstration. You can have the €6 DVB-T receivers as signal source. You can do the same with oscilloscope, or you can do this with synthetic signal. And the flowchart is exactly the same. You just have to adapt the source to whatever signal processing you want to analyze. So that's an example with oscilloscope. That's an example with DVB-T. And tomorrow during the tutorial, we'll do the same with synthetic signal. So that's really the beauty of GNU Radio flowchart, is also to be running on synthetic signal to test your signal processing techniques. Now, how does it look like? How do I implement an actual passive radar measurement? Here's an example of a passive radar measurement setup that I did for my sensors. So my sensors are working at 2.4 gigahertz. So what I did is I took a Wi-Fi emitter. My claim is that I can do this with any Wi-Fi emitter by using the electromagnetic smog that we have around us. But here, for the completeness of the experiment, the reproducibility of the experiment, I use a dedicated Wi-Fi emitter. This Wi-Fi emitter, well, I didn't want to use an omnidirectional antenna, so what I did here is I used a cantenna to be a bit more directional. This cantenna is illuminating the sensor, which is located over here. The distance is about 50 centimeters from the sensor to the emitter. And then I've got all these receivers looking at the response of this sensor. And what I want to do is I want to try to detect time-delayed copies of my initial signal. Now, in radar measurement, usually you benefit from Doppler shift, because Doppler shift will significantly improve your signal-to-noise ratio, because you're looking at signals that were not at frequency components of the emitter. Here, the sensor is static, so the sensor is sending back information at the same frequency that the signal that was used to illuminate it. So I'm not benefiting from the improvement of Doppler shift. Here, I'm just using the time delay copy, so it's just a basic cross-correlation to measure the time delay copies of my sensor. And so just to show you what it looks like, well, here if I take a signal Wi-Fi channel, 15 megahertz channel, and I take the correlation of the signal, you see here 1, 2, 3, 4, 5, 6, 7, and 8 echoes. I don't know what the ninth is here, but you have 8 echoes, which are the 8 echoes of my sensor. And, well, as I told you, I have 15 megahertz. 15 megahertz is 30 centimeter resolution, so I don't have that good of a range resolution. So what I can do is I can say, well, if I want a better range resolution, which is the inverse of the bandwidth, I want to extend the bandwidth of my measurement. But Wi-Fi is only 15 megahertz. Why? How can I do this? Well, when you do a measurement using a network analyzer, you don't measure all the frequency bands at the same time. With a network analyzer, you measure one frequency, then the other, then you continue so on, and then you take the inverse Fourier transform of your spectral characterization. Well, with Wi-Fi, you can do exactly the same. You can say, I measure Wi-Fi channel 3, channel 5, channel 7, which are not at the same frequency, and I just accumulate the Fourier domain, frequency domain components, and then after accumulating all the spectra, I take the inverse Fourier transform. And surely enough, you get again your 8 echoes with a bandwidth, which was divided by 3, because I collected 3 Wi-Fi channels. So I check here, indeed, my time resolution is inverse of the bandwidth of the signal. Now, this looks all very simple, and that's about a week worth of work. Is it so simple? Well, there's a little bit of a trick with passive radar measurement. And we heard this morning about least square weights analysis in the DOA analysis. Well, here we have to do exactly the same. The problem is that everything I talked to you so far assumes that the source is a noise source, so there is no correlation with the source. And actually, Wi-Fi is not exactly a noise. There is some correlation. So if you look at time-delayed copies of Wi-Fi, it looks a little bit similar. So if you just look at the autocorrelation, there's the blue curve here. That's the autocorrelation of Wi-Fi. And what you see, what I will show you at the end, is that the sensor signal is the little black square here. So basically, the autocorrelation intrinsic to Wi-Fi is about 100-fold stronger than the signal that will be sent back by my echoes from the sensors. And what you need is to identify what is called direct signal interference, so the direct communication from the emitter to the receiver, which will clearly overwhelm the tiny signal returned by the sensor. So what you need to do is to try to find delayed copies of a reference. So here is my reference measurement, and then I take delayed copies, so by 1 time slot, 2 time slot, 3 time slot, each time slot being one sampling period, and I try to find, is this time-shifted copy of a reference found in the measurement channel? If you're familiar with least square measurements, it's called Pseudoinverse, so that's a function in MATLAB that is quite efficiently implemented. You can demonstrate this is how Pseudoinverse is working. I don't have time to get into the details of mathematics, but at the end of the day, you just need to take 4 or 5 time delays to get rid of all the autocorrelation of Wi-Fi and to just identify the 8 echoes here, which are the zoom on this tiny thing here. So basically, when you want to do passive radar, it's just a matter of having 2 receivers, time synchronous, one of them looking at the reference channel, one of them looking at the measurement channel, surveillance channel, getting rid of a direct communication between the two, and then by looking at the correlation, you get your sensor signal. So it's not very complex, but it's working pretty well, and it can be implemented quite easily in GNU Radio through the Fourier transform analysis, as will be discussed tomorrow during the tutorial session. Now, what you want to do is, when you do this pseudo-inverse is looking at very few time delays, but you have a huge number of data. Well, typically 4,000, more often about 1 million, 2 to the 20. So you're manipulating, you're handling matrices with about 4 to 8 million elements. So do you actually need these 4 to 8 million elements? Just to give you a hint about what least square method means, let's say you have some dots with a trend, and you have many such dots, and you want to identify the trend of these dots. So this is exactly a least square fitting. Now, if you just take the black dots here, which are actually red on my screen, the black dots here are just 15 out of 100 samples. But by taking just 15 out of 100 samples, I still get a very accurate estimate of the slope of this linear fit. That's your least square fitting on some noisy samples. And what I'm trying to show you here, you don't need that many samples to do a proper least square fitting. You just take a random subset of your data, and you can do a good least square fitting. That's exactly what we did with our radar measurement. You collect a huge number of data because your signal to noise ratio during the correlation process improves as the number of samples, but during the least square fitting, you can just take a random subset, so integer random subset of your data that you've collected, and you still have a very good estimate of your direct signal interference. Not so good at short time interval, but we don't really care. We're interested in the time echoes, in the echoes located 1 to 3 microseconds. So you can do some least square fitting on just a subset of your measurements, and that will greatly improve your measurement, your calculation duration, because instead of calculating for 8 seconds, you only calculate for 80 milliseconds. So you get 100-fold calculation improvement with very little loss in terms of performance. And then, because a correlation is a linear effect, if you have phase shift due to the time delay introduced by the sensor, so basically an accurate time of flight measurement is calculated through phase measurement, well, this is the phase of my sensor, and you see that the phase of my sensor is indeed shifting as I'm cooling down. So here I have baseline, I'm cooling my sensor with a freezing spray, and then I look at the temperature going back to room temperature, freeze it again, and look it go back to room temperature. So basically, passive radar allows you to measure using electromagnetic smog, non-cooperative emitters, the response of time-delayed echoes, and in my case, these time delay are representative of a physical quantity that I want to measure. Now, just to get you interested, and I don't have time to get into the details, I just want to show you that we can do exactly passive radar, not only for range and velocity measurement, but we can do direction of arrival, as we've shown earlier with the active system, except that I'm doing this with a passive system. I have a Wi-Fi emitter. This Wi-Fi emitter is illuminating a target, and the target signal is collected not with one antenna, but with multiple antennas. And again, we've seen the theory earlier, so I don't have to go back with the details, but I have a uniformly placed linear array, so you just apply the same weighting function that we saw earlier, and so you take the setup that you have here, and what you can do is, if you have this array of sensors, you can find the sensor response, 1, 2, 3, 4, 5, 6, 7, and 8 echoes of my sensor. If you remember, this is the time characterization, 1, 2, 3, 4, 5, 6, 7, and 8 echoes. And I can say, here my sensor is located to the left. And if I move the sensor to the right, well, here you are, the sensor has moved to the right. So you have a direction of arrival information. But what is really interesting for me is that by using direction of arrival, I can separate two sources emitting simultaneously. So if I have two sensors emitting signals at the same time, now I can spatially differentiate them. You have one sensor on the left, one sensor on the right, and by using direction of arrival measurement, you can differentiate which sensor is on the left and which sensor is on the right. And if you move these sensors, again, you can detect the motion of the sensor. So basically what I wanted to show you here is passive radar needs an oscilloscope, dual channel oscilloscope, GNU radio with a Fourier transform analysis to get the correlation computed, and then direct signal interference removal. This at the moment is still done offline using MATLAB or Octave. And then you can extend the strategy of passive radar to phase array by taking direction of arrival measurements. So that's just to get you interested in passive radar and how to implement passive radar using GNU radio. So that's all the SAR processing, where you can analyze where the echoes are moving as a function of distance between these echoes. And as you can see, as the echoes are moved apart, indeed the direction of arrival indeed shows that the sensors are moving one away from the other. So that gets me to the conclusion. I wanted to get you interested in passive radar measurements. I wanted to show you that beyond passive targets such as planes, such as ships, you can design acoustic sensors as cooperative targets. We're doing this for sensor application. This is commonly used for tagging information, for identifier information. We've been using passive radar implementation using commercial off-the-shelf Wi-Fi meters. So we're using oscilloscope, radio frequency grade oscilloscope, and we have released the GR oscilloscope block, which is a very basic block. And tomorrow, Tanguy will show you how to write your own block. So using a GNU radio to collect data from an oscilloscope is really easy to implement. I showed you the basic signal processing for direct signal interference removal. And basically, I wanted to conclude by showing that you can collect physical quantities, and you can do direction of arrival measurements. So at the moment, my outlook for this work is to try to replace the radio frequency grade oscilloscope with the red Bitaya embedded board so that I can move around. At the moment, I have this big radio frequency oscilloscope, which prevents me from moving around. I would like to be able to get close to existing Wi-Fi emitters, so getting everything embedded using the red Pitaya board. And I would like to improve synthetic Kappa radar, exactly like the previous presentation that was shown. We already implemented music. Music is taking forever to run. The computation load is really heavy. Capon might be a bit better, so we want to go for higher resolution angular analysis. So we published a few of his work in the literature. And with this conclusion, I thank you for your attention. If there's any question. The mathematical details will be addressed during the tutorial tomorrow morning. So that's a bit of a story about the tutorial tomorrow. I will be very, very basic about GNU radio. I will be a bit less basic about signal processing.
So you talk about that tomorrow?
Yes, that will be the storyline of my presentation tomorrow. So we'll start slowly. Don't worry. We will not start with 20 block flowchart. We'll start with 1, then with 2, and we'll finish with 20.
I have a question. So for the directional arrival thing that you were showing, so you say you use many antennas?
Yes.
So what does that look like actually? How many antennas do you have? How are they connected?
It's a kind of a pity because you can hardly see the picture here.
Yeah. Because the thing is that the colors are in this cable are not good, so maybe you switch the cable?
So just to show you what I found fascinating, before going to Japan, I was not familiar with the fact that, again, as in the network analyzer where you have no reason of measuring all the frequencies at the same time, for DOA analysis, you have no reason of measuring all the antennas at the same time. You might measure antenna number 1, then antenna number 2, number 3, and then you do the processing of all this data that you collected. Yes. So in my case, I have my Wi-Fi emitter over here, and I have 1, 2, 3, 4, 5, 6, 7, and 8 antennas. Okay. These are 8 dipole antennas located half wavelength from a ground plane. And here I have a radio frequency switch that switches from one antenna to the other. So actually, of course, it takes a lot of time to analyze because you need to measure 3 Wi-Fi channels multiplied by 8 antennas. So when I say a lot of time, it takes 2 to 3 seconds to collect the data. But basically what it looks like is there is no reason for you to collect all the data at the same time. You don't need 8 receivers. So this is a really important consequence for me, for people who have USRP. You have one USRP, but just by using a radio frequency switch, you can measure multiple antennas one after the other, and all you're interested in is in the phase between the emitted signal and the received signal at each antenna. And DOA, as was shown earlier, is just a matter of implementing a weighting function that will compensate for the phase introduced by the geometry. So you just take this phase artifact here, which is only dependent on distance between antenna, angle of arrival, and antenna index, and that tells you what is the wavefront direction of arrival. So you just need to collect one after the other each one of the antenna, and then you do the processing on the matrix that was generated. X-axis you have antenna number, y-axis you have all the samples as a function of time.
So your switch must actually select antennas at a much higher rate than the signal you're listening to.
The data acquisition is taking a lot of time so I would say like 10 milliseconds on one antenna, collect the Wi-Fi signal. When I switch to the next antenna, I collect 10 milliseconds worth of data. So quite the opposite. The switch is very slow with respect to the signal. I just go on one antenna, I look at what is happening here. When I'm finished collecting this sensor response, I move to the second antenna. So this is why it's actually taking a bit of time, because I need to go through all these antennas, and each one of these antennas needs the time to collect data from the oscilloscope to the computer.
Okay, I see. So actually what I meant was that the switching must be faster than your environment, because if your environment is moving
definitely
at a faster rate, then you lose the...
Which is the reason why I want to switch to the red pitaya, because here I'm limited by the time transfer duration due to the Ethernet link. This is still Ethernet, but I still to initiate all the transaction between the PC and the oscilloscope, get all the data. If I believe that if I use, and Gwen wrote for me, the direct memory access block for red pitaya, I assume that if I collect the data from FPGA of red pitaya, send it through the DMA to the CPU, then I will save a lot of time with respect to transferring from the oscilloscope to the PC.
Okay.
But indeed, you're correct. I assume that the environment is static during the whole measurement.
Any other question? Thank you.